Okay, so now that we have been introduced to some two-dimensional objects and some general ways to represent two-dimensional objects, it's a good idea to look at the simplest example of a two-dimensional object in space, and that would be a plane. Similar to lines, which are the simplest example for one-dimensional objects in space, we will look at the fact that there are several different equations for a plane. And well, now that we have lines and planes, we can then talk about a few other things, such as intersections, and these intersections actually are related to systems of linear equations, so we will briefly revisit those systems of linear equations that we have seen since pre-calculus. And then once we have talked about intersections, we can also realize that intersections typically happen at an angle, and so we will investigate intersections of planes and planes, as well as intersections of planes with lines, and we will finish out with talking about distances, because when objects don't intersect, well, then they are a certain distance apart, and we may like to know what that distance is. Alright, we start with equations of planes, and well, basically the geometric idea of a plane is that a plane is determined by 3 points that don't all fall on the same line. So if we've got 1 point, 2 points, 3 points, and those don't all fall on the same line, we can even see that here edge on, even though if it had been rotated a little bit more, it would look as if they're on a straight line. Well, then these points determine a plane, right? On the other hand, okay, so how do we turn these pictures into equations? Well, we could choose one point as the base point. We could draw vectors from the base point to each of the other points, and then following first along one of those vectors, or going in the opposite direction and along the same direction and along the other vector, or opposite the other vector, gets us to any point in the plane. So if we are looking at that here, if we're following along certain direction vectors from a base point, that allows us to reach all points in the plane. If we're looking at the picture we've had before, if this here is our base point, well, then we could go over and up to reach the first point, and then up a little bit further to reach the second point. We could also go over and across, and we could also do that with vectors that are diagonal, such as the vector that connects these 2 points and the vector that connects these 2 points. All right, well, wait. If we're looking at a function such as f of xy equals y minus 2x, all the traces of that function are straight lines, right? And so that function should represent a plane, and it does. And that is something that we can see very nicely in this animation here. Here are the y traces, and the x traces are going across. And when you then interpolate that, you get a plane. And that plane, once we put the whole grid on there, looks very much like the plane that we have just seen. So we also want to know what the connection is between the geometric idea with the points and the vectors and this type of equation. And in order to do that, well, we're going to investigate actually 3 types of equations of planes, namely the 2 types that we've just alluded to, and there's one intermediate type. So, definition. The parametric equation of a plane through the point S0 with direction vectors d and w is S of u and v, so surface of u and v again, base point SU plus u parameter times the first direction d plus v, the other parameter, times the second direction w. The domain for the parameters u and v is in each case a set of all real numbers, so this is basically very much like the equation of a line, only that we have a second dimension added to it. And there's apparently no separate name for the 3 component equations of S. Remember, typically parametric equations are things that are done component-wise. Well, for planes, I didn't make the terminology. If I had, I wouldn't have made it that way, but we want to stick with standard terminology. The parametric equation is this. Okay, so what would we have? We would have a base point S0 with a position vector, and then we're saying that by using direction vectors we can reach any point. Okay, so here's the direction vector d, here's the direction vector w, and now if I start combining those vectors, I can reach parallelograms and all sorts of points that I can reach by just going in these directions and combining those, and that adds up ultimately to all the points that are in this plane that is indicated here with this dotted parallelogram. Okay, so as an example, I want us to find the parametric equation of the plane that goes through the points 1, 4, 2, negative 2, 4, 5, and 3, negative 1, 5. Alright, well, we need a direction vector, and basically I will choose the point 1, 4, 2 as the pivot point, and I will subtract its position vector of this vector and that vector to get the direction vectors. So the first direction vector would be negative 2, 4, 5, minus the pivot point 1, 4, 2, and we get negative 3, 0, and 3 here, negative 3, 0, and 3. The second direction vector would be 3, negative 1, 5, minus 1, 4, 2 as vectors. We would get 2, negative 5, and negative 7, 2, negative 5, negative 7. And then the parametric equation of the plane, surface of u and v, would just be base point 1, 4, 2, plus u times the first direction vector, negative 3, 0, 3 from here, plus v times the second direction vector, which is 2, negative 5, 7 from here. Now notice that I could have used any of these other 2 points also as my base point, but it feels nicer to use this one as a base point, because then I know that when I set u equal to 1 and v equal to 0, I end up with negative 2, 4, 5, which is the second point. And if I set u equals 0 and v equals 1, I end up with 3, negative 1, and negative 5, and that is the third point that we had on the plane. So that allows us to double check and keep track of things a little bit better. Alright, well, next definition, the vector equation of a plane. You may have wondered why we didn't call the previous equation the vector equation. Well, that's because the vector equation is what comes next, and that is the vector equation of a plane through the point S0 and perpendicular to the vector n is given by n dot s minus s0 equals 0, and that is because a plane can also be envisioned as the set of all points that are perpendicular to a certain normal vector and located at a certain height. Remember, for example, that the coordinate planes, the x, y, z planes, were the planes that were perpendicular to the coordinate axes, which could act so that the unit normal vectors could act as normal vectors for these planes. Alright, S denotes an arbitrary point on the plane, and so what we have there is we have a base point. We have a difference between an arbitrary point and the base point, so that is a vector that is in the plane, it is parallel to the plane, and that means it would have to be perpendicular to a direction that is perpendicular to the plane, and that means that n dot this direction has to be 0, which is why this defines a plane. The vector n is also called a normal vector of the plane, and if we're visualizing that, well, here's a point S0. Off of that point, we could say we've got directions d and w that are inside the plane, and that sort of defines the plane. D and w also serve here as vectors s minus s0, because w would be this point minus s0, and d would be this point minus s0. And a normal vector stands perpendicular on that plane, and therefore it would be perpendicular to any vector that is inside that plane. And so we can see here the normal vector just tells us in which directions we're allowed to go, namely the directions that are perpendicular to the normal vector, and the point S0 tells us at what height relative to the normal vector ultimately the plane sits. Okay, now of course we can take a look at an example here, and we can find the vector equation of the plane with parametric equation, surface of u and v being 1, 4, 2 plus u times negative 3, 0, 3 plus v times 2, negative 5, 7. This is deliberate. This is the plane that we had just talked about when we started with the 3 points, because I want to show how you can get from the 3 points all the way to this scalar equation, this functional representation that we've alluded to. And so the next step here would be to take the parametric equation and turn it into a vector equation. Well, how do we do that? Well, we have 2 vectors inside the plane, and we need a vector that is normal to the plane. We need a vector that is perpendicular to the 2 direction vectors. Well, when you have 2 vectors given, then there is a standard way to find a third vector that is perpendicular to both, and that is you figure out the cross product of these 2 vectors. And so that's exactly what we're going to do. The normal vector is just the cross product of the 2 direction vectors, so it'll be negative 3, 0, 3 cross 2, negative 5, negative 7. How do we compute the cross product? Well, for the first component, we blot out the first row and do a cross multiplication here, so we get 0 minus negative 15, so the first component will be 15. For the second component, we blot out the second row and do a cross multiplication. We get 21 minus 6 is 15, and remember in the second component we have an extra negative sign, so we get minus 15, so we have 15 minus 15, and then for the third component, well, we blot out the third row, we do the cross multiplication, we get 15 minus 0, which is 15. This is completely accidental. I just picked 3 points to start working with. I had no idea that these would come out to be, that the normal vector would come out to have the same component in x, y, and z except for a negative sign. But when it came out, I thought, well, there's no point in artificially changing that. Just don't expect these numbers to always work out to be the same. Alright, so now the vector equation then is 15, negative 15, and 15 dot arbitrary point in the plane, x, y, z, minus base point 1, 4, 2, and that's supposed to be equal to 0, and that's already it. So that's not that bad either. And finally, the scalar equation of a plane, and here's where we're going to be tied to three-dimensional space. The other equations actually were arbitrary equations with arbitrary vectors that would work in higher dimensional space also, but the scalar equation of a plane in three-dimensional space is of the form a times x minus x0 plus b times y minus y0 plus c times z minus z0 equals 0. You can see the similarity with the vector equation here because basically x0, y0, z0 is a base point in the plane, and a, b, c, well, basically we have a, b, c as a vector dot product with x minus x0, y minus y0, z minus z0 has to be equal to 0, so these guys here should be the components of the normal vector, and we're going to see that also in the examples. If you simplify that, you could also write this as ax plus by plus cz equals d, and again a, b, c most likely are the components of a normal vector, and we're going to verify that as we go through an example. X, y, z denotes an arbitrary point on the plane, so those are these arbitrary coordinates. Alright, now another thing you can see here is of course that this equation is exactly the kind of equation that we were dealing with when we were working with systems of linear equations, and that is the connection that we're going to make later on also. Alright, so as an example, find the scalar equation of the plane with vector equation 1, negative 1, 1 times x, y, z minus 1, 4, 2 equals 0. That is the equation of the plane that we had just in the previous example. I just divided everything by 15, which is not a problem because the right-hand side divided by 15 is 0, and the left-hand side divided by 15 gives us this handier normal vector. How do we turn this normal equation into a scalar equation? Well, we just multiply things out, right? 1, negative 1, 1 dot x, y, z minus 1, 4, 2 equals 0. That's the same as 1, negative 1, 1 dot x minus 1, y minus 4, z minus 2 equals 0, which is the same as 1 times x minus 1 minus 1 times y minus 4 plus 1 times z minus 2 equals 0. That already looks like one of the possible scalar forms of an equation for a plane, and we're just going to multiply it out and bring the number over to the right side. So we're going to have 1 times x, so x minus y plus z on the left, and then we've got here, let's see, negative 1 plus 4 is 3 minus 2 is 1, so we're going to get a negative 1 on the right side, so we get x minus y plus z equals negative 1, which is actually pretty simple. Alright, well, so that tells us how to go from 3 points all the way through the scalar equation of a plane. So basically, if we want to convert between the different forms, if I have 3 points, or if I have the parametric equation, and we're supposed to find the scalar equation, I can just pass through the vector equation as an intermediate stage. Now, parenthetically, as a remark, you could also, if you are given 3 points, you could set up a system of equations for a, b, c in the equation ax plus by plus cz equals 1. Okay, you might say here, wait a minute, I said previously that the equation was ax plus by plus cz equals d, and yes, that is correct. That is also another way to write it down. But I could take that equation, and as long as d is not equal to 0, I could divide by d, and if I divide by d, I end up with a 1 on the right-hand side and new coefficients on the left. So if I have 3 points, I could set up 3 equations using x1, y1, z1, x2, y2, z2, and x3, y3, z3. 3 equations for the 3 variables a, b, and c, and I could solve that. Otherwise, this geometric transformation really works best as far as I can see. I go to the parametric equation, which wasn't that bad. From the parametric equation, I get the vector equation, which is not that bad. And from the vector equation, I get the scalar equation, which again is not that bad to compute. All right, how do we get back? Well, let's take a plane, and I'm already giving this actually as a function, which is something I can do if I could just solve for z, and that would be another way in which a plane could be given. So for the plane z equals f of xy equals 2 plus 4x plus 7y, I want to find the vector equation and the parametric equation. That tells us how to get back, because, well, if I were to ask you to find 3 points, you would just choose xy equals 0, 0. You could choose xy being 1, 0, and xy being 0, 1, and compute those 3 points, right? So that's not that hard. The vector and parametric equations are what we want to transform back to, and we want to transform back to them in a meaningful way. So first, let's find the vector equation. Well, z equals 2 plus 4x plus 7y. If I bring the z over, or if I bring the 4x plus 7y over to the left, either way, I want to have my variables on one side. And so I could say this is 4x plus 7y minus z plus 2. So I brought the z over and then switched sides. Well, the 2 I can absorb into one of those variables, and if I have factors in front of anything, I would just have to factor things out the right way. So for example, if I wanted to combine the 2 with the x, I would end up with 4x plus 1/2. But here it's actually very convenient. I can say 4x plus 7y minus z minus 2 equals 0 in parentheses. And then I realized that that is just the same as taking the vector 4, 7, negative 1 times x, y, z minus 2 equals 0. So I'm recognizing a dot product here. And that's, of course, just 4, 7, negative 1 times x, y, z minus 0, 0, 2. And here is the vector equation of this plane, right? So one thing that we always want to remember when we are looking at scalar equations, and again, remember, I'm not one who is very big on memorization, and in some ways, if you just understand how the equations transform into each other, you don't have to memorize it, but these coefficients here in the scalar equation, including the negative 1 that is sitting here and is indicated by the negative sign, these coefficients are the normal vector, x component, y component, z component. So that's how you can always get the normal vector back, and you just have to digest that last number in some way, and typically you just pair it with one of the variables. Okay, parametric equation. The normal vector, well, is 4, 7, negative 1. We knew that already, and for the parametric equation, we need 2 vectors that are perpendicular to the normal vector. Now, that sounds hard, but actually there are infinitely many vectors inside that plane that are perpendicular to that normal vector. We just have to generate 2. Well, what do we know about perpendicular vectors? Vectors are perpendicular if and only if their scalar product works out to be 0. How can I generate a vector whose scalar product with 4, 7, negative 1 is equal to 0? Well, I could multiply the negative 1 with 0. That way I don't only have to worry about 2 components. And then I could multiply the 4 with negative 7 and the 7 with 4. And so that would give me a parallel vector. And so D, I actually multiplied the 4 with 7 and the 7 with negative 4. That may not have been what I've said, but it doesn't matter where I put the negative sign. So one vector that is perpendicular to this normal vector is 7, negative 4, 0. You can verify that very quickly with the dot product. And then I have to make sure that those 2 vectors are not parallel, right? Because if I use the same direction twice, I think my highlighting does just not want to work. Okay, here we go. Non-parallel. That's the other thing we have to be very careful with. And well, one way to fail here is to use a vector like 14 and negative 8 now, because then I'm going in the same direction twice and I'm actually ending up with a line that has a really awkward parametrization. Well, one way to make a vector non-parallel to this one is to now make sure that I've got a non-zero third component. So I could go, for example, with 4 in the z component, 1 in the x component, and 0 in the y component, and I think that's what I did. Yeah, I have 1, 0, 4, and then 1 times 4, 4 times negative 1. If I work out the dot product, that's equal to 0 also. So these 2 vectors are perpendicular to the normal vector. They are not parallel to each other. And if I want a base point, well, I just plug in 2 points. I could plug in 0, and so I get when x is equal to 0 and y is equal to 0, then z is equal to 2, so 0, 0, 2 is my base point, plus first parameter times first direction vector 7, negative 4, 0, plus second parameter times second direction vector 1, 0, 4 equals 0. So we have seen that even though we have 3 different kinds of equations for planes, we can translate back and forth between these kinds of equations. And we can use that to our advantage when we compute intersections. Okay, so let's compute the intersection, compute the intersection of the plane that is given in the vector equation as 3, negative 1, 2, dot point on the plane minus 0, 1, negative 4 equals 0, with the line that is given in symmetric equations, x minus 2 over 3 equals y equals 1 minus z over 7. And, well, the first thing we really need to do is we need to compute the right equations of those things. So maybe I should have put a simpler example here first, but basically one of the things that is the key to working with lines and planes is to know which equations do what. For example, if I had both the parametric equation of the plane and the vector equation of the line, I could just set the two equal. I would get 3 equations in the 3 parameters, and I could solve that. But actually, the quickest way to compute the intersection of a line and a plane is to use the scalar equation of the plane, because that scalar equation of the plane uses x, y, and z, and then use the vector equation of the line, which gives us x of t, y of t, z of t, and then just plug x of t, y of t, z of t into the scalar equation of the plane. That gives us one equation in one variable, which is a whole lot easier to solve. And that's exactly what we're going to do here. So let's find, and note that in many cases, and if you work with my book, you'll see that you might even curse me for it. I've been really good at setting up homework problems where you are supposed to convert to the right type of equation first, and that is just method to my madness here. I want you to be able to fluently convert to these between these types of equations, but basically in many cases, in many problems, whether we talk about intersections or also angles of intersection, the first step is to convert to the right type of equation so you have the data available that is appropriate for the computation. So let's first find the scalar equation of the plane. Well, 3, negative 1, 2 dot x, y, z minus 0, 1, negative 4. If you work that out directly, that's 3 times x minus 0, as we have here. Then we have minus 1, so minus 1 times y minus 1, which is what we have right here. And then we have plus 2 times z minus 4, z minus minus 4, which is z plus 4, which we have here. Then we just have to multiply it out. We get 3x minus y plus 2z, and we have 0 plus 1 plus 8, that's 9, and that can be brought over as a negative 9 to the other side. So we end up with 3x from here, minus y from here, plus 2z from here, equals minus 9, which is all the scalars collected and put to the right side. If we're looking at the symmetric equations, here's again something that we have to remember, and that is the symmetric equations, you turn them into the right form. You get x minus 2 over 3, which we had. The y is a y minus 0 over 1. And I probably also should have switched things around here. This is actually a z minus 1 over negative 7 if you want to write it out. And that means that the direction vector has x component x, x component 3, y component 1, and z component negative 7, because we would have to write this as z minus 1 over negative 7. And so that means that the equation of the line would be some point on the line, and of course a point to choose would be x is equal to 2 makes this equal to 0, y is equal to 0 makes the second one equal 0, and z equals 1 makes the third one equal to 0. So 2, 0, 1 is a point on the line, and the direction vector is 3, 1, negative 7, as I already mentioned, the negative sign coming from the z here. Okay, so we have the equation 3x minus y plus 2z equals negative 9. And we've got the vector equation of the line 2, 0, 1 plus t times 3, 1, negative 7. Okay, so now that means I would take 3 and I plug in 2 plus 3t for x. I would have minus y, so that would be minus t. And I have 2z, which would be 2 times 1 minus 7t. and that's exactly what we're doing. 3 times 2 plus t times 3, minus y, which is just t, plus 2 times 1 minus 7t, 2 times 1 plus t times negative 7, 1 minus 7t. Right-hand side is still equal to negative 9. Well, that is one equation and one variable, and it's linear, so it can't be that hard. 3 times 3 is 9, minus 1 is 8, plus negative 14 will be negative 6, which is a minus 6t. And the other one, 3 times 2 is 6, minus nothing from here, plus 2 is 8, that's the 8 here. And we've got the negative 9 on the right side. So now we solve that, we get negative 6t equals negative 17. T equals 17 over 16. Not pretty, and again I was thinking, well, should I make the numbers pretty? But in general the numbers aren't going to be pretty, and actually now that I have the parameter, all I have to do is plug 17 over 16 in here to get my answer. And even though the fractions may not be that nice, it can't be that bad either. So L of 17 over 16 is 201 plus 17 over 16 times 3, 1, negative 7. And so what would that be? Well, let's see. 17 over 6 times 3 would be 17 over 2, plus 4 over 2 would be 21 over 2. That's what we have here. 1 times 17 over 6 is 17 over 6. And this one is the nasty one. Well, first of all, we know it's probably going to be negative because there's a lot of negative stuff here that's not going to compensate for that 1. Okay, so 17 times 7. 70 plus 49 is 106. 70 plus 49 is 119. So negative 119 plus 6 is a negative 113 divided by 6. Yeah, that works out too. And, well, that is the answer. That is the intersection point. Now, there are other possibilities. The line could run parallel to the plane, in which case we wouldn't get a solution for t, and we wouldn't get a point. Or it could also be that the line is actually inside the plane, which would mean that arbitrary t's would work, and that would mean that the equation on the previous panel would just be solvable for any t. Visually speaking, well, here's the situation. Here's our plane, here's the line cutting through the plane, and here's the point. And basically what I have done is I have just used my computer algebra system, stuck in the equation of the plane, stuck in the equation of the line, and then put in the point and made sure that, yeah, okay, they really all hit in the matter in which it was advertised. This point really is the intersection point. When we talk about intersections, we could also compute the intersection of two planes. So let's take a look at the planes 4x minus y plus 2z equals 3, and the plane negative 2x plus 4y plus 3z equals 9. If I want to compute the intersection of these two planes, hey, that looks very much like a system of equations, two linear equations for three variables, and that's indeed what it is. So what I can do here is, well, the most obvious thing to do would be to take 2 times the second equation and subtract it from the first equation. That would give us no x's. It would give us negative 9y. But actually, I add, sorry. I add, I'm not quite focusing right here. Okay, I add the second equation to the first. I add 2 times the second equation to the first one. And so that would give me negative 4x plus 4x, so the x's are gone. And then I have 2 times 4y is 8y minus y is 7y. 2 times 3z plus 2z is 8z. And 2 times 9 plus 3 is 21. And that's already it. Well, we know from pre-calculus how to continue. We have one parameter that we can simply choose. And so if I set z equal to t, well, then I get that I can solve for y here, and that would be 21 minus 8z divided by 7. And, well, then because z is equal to t, that gives me that y is equal to 21 minus 8t over 7. And for x, well, for x I solve, which one did I solve? I solved the first equation for x, and that would be 3 plus y minus 2z, as we have right here, and then divided by 4, which is, of course, this 4 from up here. And now I know z is equal to t, so that's not that bad, and y is equal to 21 minus 8t over 7. Yeah, that can get a little bit uglier. But if we just plug it in, I get 3 plus 21 minus 8t over 7 minus 2t. And what I wanted to do here is I wanted to put it all on a common denominator. Okay, so I first just put everything in the numerator on a common denominator. And that would mean that once I work out the division, I get a denominator 28. And common denominator for the numerator, well, 3 times 7 is 21. So 21 plus 21 will give me 42. And negative 14t minus 8t would be negative 22t. So I end up with 42 minus 22t divided by 7 times 4, which is 28. And I see here that I can cancel a 2. So I end up with 21 minus 11t divided by 14 after I cancel a 2. Well, I can pull that over to the to the next slide. And these are now the parametric equations of a line, which I can turn into the vector equation of a line. And when I do that, I've got x puzzled apart, and I know 21 over 14, that's the constant part, and that's, of course, 3/2. And then I have plus t times negative 11 over 14, which is what I have here. For y, 21 over 7 gives me 3, and then I have plus t times negative 8 over 7, which is a negative 8 over 7 here. And z is 0 plus t times 1. And so this would be the vector equation of the line of intersection. And this is, of course, also something that people have told you in pre-calculus. The intersection of two planes is a line, and that is what we can also see if we're looking at the first plane here, second plane here, and then here is the line of intersection. And that, of course, now brings us to the point where we may just quickly want to talk about systems of linear equations. Because when we talk about systems of linear equations, in pre-calculus, yeah, we talk about planes, but technically, until we hit this stage of multivariable calculus, we really haven't explained why those equations are equations of planes. Why now we just see it, they simply form an equation of a surface in three-dimensional space that happens to be a plane. So now we can look at systems of linear equations again, and when I have three equations with three variables, there is the possibility to have a unique solution, right? And that's where you were told in pre-calculus, that's because the three planes just intersect in the right way, and that is indeed what is happening. If I take three planes that just aren't in any way parallel to each other or non-intersecting in some way, then no matter how I rotate this, I will not be able to get the intersection of these three planes to come out anything more than this point, and that's what it means to have a unique solution, right? Okay, now we could also take a look at what happens when we've got infinitely many solutions. I have to just go to a different MathCAD sheet, and so when I have infinitely many solutions, basically what happens is that my three planes are all intersecting in the same line. So if you're looking at what we had previously, where two planes intersected in a line, if I have a system of three equations with three variables, well, two planes will still intersect in a line, and the third plane will just have to go through the same line. And that's the kind of thing that you can also see if you view that on edge. You realize that this is very similar to a pathological situation that you could also have in 2 dimensions, where three lines intersect in the same point, right? So this kind of rotating things literally here in a computer algebra system, this is the kind of thing that I want you to also practice mentally. You want to be able to visualize a situation and then rotate it in your mind in the right way to see the relevant angles and things, because remember that ultimately we're also going to talk about angles of intersection. Okay, in terms of systems of linear equations, the other thing that could happen is that you've got three equations, three variables, and no solution. And, well, yeah, that's the kind of thing that could happen when you have three planes, and these three planes are just lining up in such a way that the lines of intersection are parallel. Of course, from this angle you can't quite see it, and it could be that we chose an awkward box where this plane has a slight tilt towards the back that ultimately makes it intersect outside of what we're seeing. But if we view this situation edge on, and here's where I just need to be able to rotate it, right? If we view this situation edge on, we can see that actually as we are viewing these planes edge on, these lines of intersections really turn into points, and that means that these lines are parallel to each other as we go infinitely far away. Something that we're also seeing here as a by the way, which we're going to use in the geometry in just a second, and it's very valuable to think about it that way, is that when you view a plane edge on, the plane looks like a line, and only if you rotate it out you see the plane again. All right, so that was a quick interlude on systems of linear equations. Now, we talked about intersections. Well, when you intersect stuff, intersections will happen at an angle. So we'd like to know the angle of intersection of two planes that intersect. And, well, what would we have? We would have one plane here, we call that thing P1. We would have a second plane here, we would call that thing P2. And then the angle of intersection between these two planes is given right here. Well, that can be a bit challenging to figure out because, as we have seen, and I'm going to go back to just the one with 3, if we're looking at the angle of intersection, we have to look at the planes the right way to get exactly this angle of intersection or exactly this angle of intersection. Let's focus on this plane and that plane. If you view that plane in a different way, it's really hard to figure out between what objects to measure that angle here, right? Not to mention that they look like that they've got a pretty large angle between them, and when you rotate them the right way, it actually turns out that the angle isn't that large after all. It certainly is even smaller than 90 degrees here. Okay, so, well, let's think back. What kinds of objects do we have between which we can compute angles easily? We have vectors. And if we're looking at planes, we can look at the vector equation. We realize the vector, the normal vector of the first plane, n1, stands parallel to the first plane, p1. The normal vector n2 of the plane p2 stands perpendicular to the plane p2. And so that means that this situation of P1 and P2 viewed edge on is just rotated 90 degrees in the normal vectors, which means the angle between the normal vectors is this angle alpha. Here's where we have to be careful. It could be that one of the normal vectors sticks out the wrong way, but that's summarized pretty easily. Basically, the angle of intersection between the two planes is equal to the angle between the normal vectors, or it is its supplementary angle. So basically, to compute the angle of intersection between two planes, we get ourselves a normal vector, compute the angle between the normal vectors. If that angle is smaller than 90 degrees, then it is the angle between the planes, because we want to report the smaller angle as the angle of intersection. We don't want to report the larger angle. And if the angle between the normal vectors turns out to be larger than 90 degrees, well, then it happens to be this angle over here, and the supplementary angle is the angle that we are after because we want to report the angle that is smaller than 90 degrees. All right, so as an example, compute the angle of intersection between the planes 4x minus y plus 2z equals 3 and negative 2x plus 4y plus 3 equals 9. Okay, again, one of those problems where we need the normal vector. We are given the scalar equation. Well, hey, we can work that out because we know that the normal vectors are what we get if we just look at the coefficients in front of x, y, and z. So the first normal vector is 4, negative 1, 2, 4, negative 1, 2. And the second normal vector is negative 2, 4, 3, because, yeah, that's what we have right here. All right, so we need to compute the angle between the normal vectors. Well, we know how to compute the angle between vectors, so in some ways we can say the rest is just computation. I just didn't put my green box on there. Take n1 dot n2, that's 4, negative 1, 2, 4, negative 1, 2, dot 2, negative 2, 4, 3, from right here. Okay, so that would give us negative 8 minus 4 is negative 12 plus 6 is negative 6. Yeah, negative 8 minus 4 plus 6, that's negative 6. Then we need the magnitude, so the norm of the first normal vector is the norm of 4, negative 1, 2, which is square root of 16 plus 1 plus 4, which is the square root of 21. 16 plus 4 is 20 plus 1 is 21. The norm of n2 is the norm of negative 2, 4, and 3, which would be square root of 4 plus 16 plus 9, so that's the square root of 20 plus 9, which is the square root of 29. The angle alpha would be the arc cosine of n1 dot n2 divided by norm n1 times norm n2, which would be the arc cosine of negative 6 divided by square root 21 divided by square root 29, and that's of course something that you work out with a calculator. You can work it out in radians as well as in degrees. I chose to give the answer in degrees here. It's 104.07 degrees approximately, and that means that the angle between the planes is approximately 75.93 degrees because it's got to be supplementary since this one was greater than 90 degrees. Okay, So that's really not that bad, and again, it's this principle that we have in multivariable calculus. We're going to continue reusing stuff that we know, right? You already know how to compute the angle between vectors. We now just work that out in a different context. All right, if we want to look at this, well, I say rotate to see the angle, so I've got a MathCAD file here for the intersection. So the angle between two planes, here are these two planes. The picture is a little bit ugly looking, and that is because I need to set it up in such a way that we actually have equal scales on all three axes, because otherwise the angle is going to be distorted. The first picture that I drew here, I thought, man, that angle just doesn't look right. And that was because I didn't have the same scales. But if once we have the same scales and we rotate things around, we can see, yeah, that looks very much like a 75-degree angle, because it's really, really close to a 90-degree angle. And I think, if necessary, I could align a protractor with this, and it ought to come out modulo the perspective feature that makes this actually look prettier ultimately. Modulo the perspective feature, this ought to be 75 degrees here. Okay, we move on. And the other thing that we can, or the other situation in which we can compute the angle of intersection, is that we've got a line and a plane. How on earth do you work that out? Well, the idea is really to see the picture. And I mean, as I've been preaching all along, as I've been throwing these harder visualizations at you, I want you to work on seeing pictures in your mind. So if I have a line and a plane, I ought to be able to visualize it. Here's my plane, P, and here's my line, L. And then here's an intersection point, and that means the angle between the two is right here, and I call that thing theta. Now here's a problem, because I don't know from which point or which line to measure that angle, right? I mean, I could now find the projection of the line into the plane in some way, and then find the angle between those two vectors, but it turns out actually that the normal vector, again, is going to be very helpful. So, first of all, for the line, we've got the direction vector, and that's the vector v. Well, for the plane, we've got two direction vectors, but those actually are just helpful in if we need to finding the normal vector. So the normal vector of the plane is right here, and we can see that this angle between the normal vector of the plane and the direction vector of the line, that's actually pi halves minus the actual angle between line and plane. Or if the normal vector sticks out the wrong way, or if the direction vector of the line goes the other direction, then we would compute this angle here, and this angle turns out to be pi halves plus theta, because we would have this right angle here plus the angle theta, which is also, of course, sitting down here below the plane. So what this means is that the angle between the line and a plane is complementary to the angle between the line and the normal vector. Sum is 90 degrees, or it exceeds that angle by pi over 2, and I looked things up and I couldn't find a name for that. But so basically what you have is, again, you just compute the angle between the direction vector of the line and the normal vector of the plane. Sorry about the highlighting there. And if that angle is between 0 and 90 degrees, then you have to subtract that off of 90 degrees in order to get the angle between the line and the plane. And if the angle is greater than 90 degrees or pi halves, well, then you subtract 90 degrees or pi halves off of that to get the angle between the line and the plane. So this is something that you could memorize, but seeing the picture is a lot more important, because that allows you to recreate this kind of stuff. In terms of an example, well, find the angle of intersection between the plane 3x minus 2y plus 4z equals 1 and the line x minus 2 equals 3 minus y equals z over 3. And yeah, that Schroeder guy, he just never gives you the right equations. Well, what do we know with it? We know that the normal vector has got to be 3, negative 2, 4, and that's what it is. And the direction vector of the line, well, that was the stuff that we divide by as long as we make sure that the negative signs work out right. So that should be 2. And then here, this is divided by 1, but remember the y is negative, so it should be negative 1 in the y component. And the z minus 0 over 3 should give us a 3 in the z component. And that's exactly what we get, 2, negative 1, 3. Once we've got that, the rest is just computation. Here's that green box that I hope will ultimately make you happy, because, well, I mean, all we have to do is compute an angle. We know how to do that, right? So, in dot v would be 3, negative 2, 4, dot 2, negative 1, 3. Double check, yeah, 3, negative 2, 4, 2, negative 1, 3. Those are the right vectors. And that would give us 6, plus 2 is 8, plus 12 is 20, right? And then we need the norm of the normal vector. So that would be the norm of 3, negative 2, 4. So that would be square root of 9 plus 4 plus 4, which would be 9 plus 4 plus 16, sorry. And that would be the square root of 29. And the norm of the direction vector of the line, the velocity vector, would be the norm of 2, negative 1, 3, which would be the square root of 4 plus 1 plus 9. So that would be the square root of 14. That would mean that this angle, auxiliary angle alpha that we need, would be the arc cosine of n dot v over n norm times v norm. So that would be the arc cosine of this 20 divided by square root 29 times square root 14, which is what we have down here. And that is something that you work out with a calculator. Of course, it ends up being approximately 6.9825 degrees. That's smaller than 90 degrees, so we have to subtract it off of 90 degrees, and the angle between the line and the plane is approximately 83.0175 degrees. That is something that you can actually work out in your head. Okay, so what would that look like? Well, let's look at it. That is the last MathCAD file that I want to show you. Okay, here's our plane, and here's the line, and again, I have to set up in such a way that I've got equal scales on everything. And for planes and lines, just looking at it from an angle is not enough, because if I rotate this the right way or the wrong way, I can change that angle, right? If I rotate this around here, at some point in time, this is almost going to look like a right angle here. And of course, with an angle that's 83 degrees, that's pretty close to being done. But see, previously, it looked like this was the smaller angle. And if I rotate it the other way, all of a sudden it looks like this one is the smaller angle. So here's where visual inspection alone is not good enough. You really have to rotate this the right way to actually capture the angle. And that is because when you measure the angle between the line and the plane, you don't exactly know from where to project your angle to. That is something that you could work out with the projection of the line into the plane, but that's not something that we're going to get into. We have a way to compute the angle between a line and a plane when they intersect, and that's good enough for us. Okay, so, well, what else can happen? We can talk about distances, because when objects don't intersect, they are a certain distance apart. It could be that two planes are parallel. It could be a line is parallel to a plane. And so when we want to measure the distance, well, when objects are parallel, then basically you could just look at a point on one object and measure the distance to the other object. And when that happens, we remember just that the shortest connection is always the connection that is perpendicular to the point, plane, or the line. So theorem, if P is a point and X is a line or a plane, then the point C on X is as close as possible to P if and only if the line segment that connects P to this point C intersects X at a right angle, so it's perpendicular to X. How do we know that? Well, let's look at our object X, and remember that this could be a line, but it could also be a plane that is viewed edge on. Here is a point, and well, now let's take a look at an arbitrary point on the line or the plane. If that point is so that the connection between P and the point in the line or plane does not intersect the line or plane at a right angle, well, then we could also project the point down at a right angle. And if we do that, then we get a right triangle here. And we can see that this distance to this point for which the connection does not intersect at a right angle is longer than the distance to this point where the connection does intersect at a right angle. And so that means that the point for which the line segment from the point to the plane intersects at a right angle is closer to the point of the plane than any of the other points, and that's exactly what we wanted to prove here. Okay, so that means we could now actually derive a formula, and there are now plenty of formulas for distances. There could be the formula for the distance between a point and a plane, and that's the one we're going to derive. Here it is. There are also formulas for the distance between two planes, for the distance between a plane and a line, for the distance between two lines, and for the distance from a point to a plane. And all those just require certain kinds of visualizations, we're just going to demonstrate what those visualizations are with this derivation here. So I claim that the distance from the point P to the plane capital P is P minus P0 dot normal vector of the plane divided by the length of the normal vector, which is just the component of the distance P minus P0 in the direction of the normal vector n. It's where P0 is the base point for the plane and n is the normal vector for the plane, and of course P is the position vector for the point. Proof? Well, let's look at our plane viewed edge on. Then we've got a point P0 on that plane, and we have the point P off the plane. And we know that the point that is obtained by going at right angles down from the point P to the plane, that's the point that is closest to the point P, and that's the point C. And of course, this distance here is parallel to the normal vector of the plane. Well, we can get a right triangle that also involves P minus P0, which is the vector that goes from the point on the plane to the point off the plane. And well, now I can also make a right triangle over here if I project everything across with the normal vector being here. But now I realize that this angle theta is the angle between the normal vector and the vector P minus P0. And so I know that the cosine of this angle is the distance from the plane to the point P divided by the length of P minus P0. So that's what we have. Cosine theta is P minus C, the distance from P to the plane, divided by P minus P0. So that's the distance from P to capital P divided by P minus P0. On the other hand, the cosine of theta is also the angle between P minus P0 and the normal vector. The cosine of the angle between P minus P0 and the normal vector. So it's P minus P0 dot n absolute value divided by P minus P0 divided by P minus P0 norm times n norm. I'm taking the absolute value here because ultimately what I am interested in is not whether the normal vector points downwards or upwards, and I know that this angle here will be smaller than 90 degrees if I'm just pointing the normal vector in the right direction. Alright, and so now this is something I can solve for the distance between P and the plane. So we have the distance between P and the plane divided by P minus P0 norm is P minus P0 dot n absolute value divided by P minus P0 norm times the norm of n. And that of course just tells me that the distance from the point P to the plane capital P is the absolute value of P minus P0 dot n divided by the norm of n, and that is exactly the definition of the component of P minus P0 divided by n. And the rest is just computation. Basically, I'm not going to insult you here. If I gave you an example that says compute the distance between this point and this plane with the normal equation given, well, what you would do is you would just find your P0, you would find your n, you would plug things in, you would do the computation. There's nothing there, right? You just do that and it's okay. There are various other formulas for distances. I think there's at least one more formula for the distance between a point and a plane, and I would want you to mainly read through the derivations and then work out the exercises for the homework. If you have to look up the formulas and then just check with your teacher whether your teacher wants you to memorize the formulas or not. I haven't quite made up my mind as to how much I would want students to memorize in any of my classes there, but that's something where you just have to find out how much you need to memorize. The main thing is you want to be able to see the visualizations. You want to be able to understand the proof that we had on the previous panel, because it is just a neat visual skill that can ultimately also help you to rederive all the other formulas that are there, and that ability is a lot more important than having another couple of formulas in memory. So here's where I'm on a soapbox. I'm going to get off that soapbox and let you get to the homework. What I'd like to say then again is just repeat, better safe than sorry. If you haven't memorized the formulas, and check with your teacher if your teacher feels that you need to memorize them, and if your teacher feels that you need to do that, well then you just would be like me, you'd have to bite the bullet and do it. Okay, I'll let you two go to your homework. I'm starting to tie up my tongue and knots also. It's been a long presentation. Have fun working your examples.